Now, the next section of this chapter has to do with what we call surds, okay? And you would again have met these perhaps in a limited way for your junior cycle maths. But surds are nothing more than irrational numbers. So surds are things like root 3, root 2, root 5, root 7. We've already met root 2 and root 3. If you remember when we were doing proof by contradiction that root 3 is irrational. So if root 3, root 5, root 7, root 11 and so on, if they're surds, then surds are irrational numbers. Okay, so just keep that in the back of your head as we go into this section here. So a surd is basically a root. That's all it is. Root 3, root 2, root 5, root 7. But it's the root of a prime number. The root of a prime number that simply cannot be written as a fraction. So therefore surds are irrational numbers. Any number in the form of the nth root of a, which cannot be written as a fraction, is called a surd. Now any number full stop that cannot be written as a fraction is irrational. Okay, just keep that in mind. We've met those already before. So that's an irrational. Surds are, as we said, irrational numbers. Root 2, root 3, root 5, root 7, root 11 and so on. Now why do I not include root 9 there? I don't include root 9 because root 9 is 3 and 3 is rational. Okay, so really at the end of the day, surds are the roots of the prime numbers. That's basically it. There are only two things to remind us about, or to remember about surds, and that is the following. Look, if you have any two roots that you're multiplying by one another, you can join the root as the root of the product. So root A times root B is equal to root AB, meaning if I'm multiplying root 5 by root 7, say, okay, that's easy. You just keep the root and multiply the two numbers, root 35, that's it. And likewise, for division, the same type of thing applies. If you're dividing two surds, well then you simply get the surd of the fraction. And again, just an example there, root 7 divided by root 3 would be the same as root 7 over 3. So for products like this, you can join the root and put the product underneath. And for quotients like that, or for divisors or fractions, whatever you want to call them, you may simply put one root sign over the entire fraction. Surds can be simplified. Now this is extremely important. Do you know who your best friend is going to be in this particular section? Calculator. Because when you tap in surds and press equals, they will always give you the simplified version. Okay, now because you're supposed to be able to do these in your head, but if you tap in root 20 on your calculator, it won't give you back root 20. Try it. It'll give you back 2 root 5. Okay, I'll explain why in a moment. Surds can be simplified. So just because they throw a surd at you doesn't mean that you have to use it in the form it's given. I would suggest every time that you're given a surd that you test first of all on your calculator to see, can this thing be simplified? So for example, take root 32. Root 32 is the same as root 16 times root 2. Okay, now that comes from the previous property a moment ago we just looked at, that if you have the square root of a number, you can actually still write that down as the roots of their factors. Okay, so 32 is 16 by 2, so therefore root 32 is root 16 by root 2, but we do know what root 16 is. Root 16 is 4. We do not know what root 2 is because it's irrational. All right, so therefore you just leave it alone. If it's an irrational number, you leave it as root 2. So therefore work out what you only can work out, meaning root 32, think of it this way, root 32. Well, first of all, 32 is equal to 16 times 2. So therefore root 32 is the same as root 16 times root 2, which is 4 times root 2. And I do not know what root 2 is, so I don't bother even thinking about it. I just leave it down as its own symbol. You should make yourself familiar with at least the first 16 squares. Now you should be able to rhyme these off, okay? If you want to really get through this surdal section quite quickly, learn off the first 16 squares. And just in case you don't have them, there they are, okay? You should at least know now by junior cert the first 12. Add on the next 4. Add on 13, 14, 15 and 16. 13 and 14 are easy to remember. 13 is 169 and 14 is 196. 15 is 225 and 16 is 256. Okay, so just know what the numbers are, the squared numbers, so you can recognize them when they're at play, maybe hiding inside a larger surd that can be simplified. So here's an example. Simplify the following. Root 50 plus root 8 plus root 32. Now look, an awful lot of algebraic rules that exist for x's and y's also exist for surds. For example, root 50 plus root 8 plus root 32. The first one is of family root 50. That's the surdal family root 50, root 8, root 32. the numbers underneath the root signs don't match, so I can't add them as they are. Now I could go to my calculator, of course, and tap in root 50 plus root 8 plus root 32, and it will give you the answer. But just to get a bit of logic behind this, where does the calculator get the answer from? And here it is. First of all, think about root 50. Is there any one of those square numbers that is a factor of 50? And very quickly I'll say, yeah, 50 is 25 times 2, see? Which means root 50 will then be root 25 times root 2. What about 8? Is there any square number that is a factor of 8? Yeah, 4. 8 is 4 times 2. So therefore root 8 is root 4 times root 2. And lastly, 32 has as a factor the perfect square 16, the square number 16. So that's 16 times 2. So therefore root 32 is root 16 times root 2. Now take the three pairs as they are given to you, like that. What does this come down to? We do know that that is 5. We do not know what root 2 is. Leave it alone. Root 4, 2. We don't know root 2 because it's irrational. And lastly, 4, root 2. And what was I told to do to them? Add. So you see where the algebraic XY thing comes in? You're now adding surds of the same family. What do we mean by that? Root 2, root 2, root 2. They've got the same tail, for want of a better phrase. Okay? So you've got 5 root 2 plus 2 root 2 plus 4 root 2. That's the same as saying something like this. 5x plus 2x plus 4x. As long as they all have the same tail or the same ending, you can add them together. 5 root 2, 2 root 2, 4 root 2. Well, 5 and 4 is 9, 2 is 11 root 2. So that's where the simplification process comes in. Now, of course, tap that into your calculator, you'll get it. But sometimes the calculator with surds will rather give you a decimal over a surdal representation. And when you're dealing with surds, really, if the question begins in surds, you should give back your answer in surdal form. Okay, so that's where we get that from. Okay, so check each surd as we said already for simplification. Root 50, well, check 50 first. 50 contains a square 25. 8 contains a square 4 as a factor, and 32 contains 16 as a factor. So you rewrite root 50 as root 25 times root 2, root 8 as root 4 times root 2, and root 32 as root 16 root 2. And then all you've got to do is simplify them down. 5 root 2, 2 root 2, and 4 root 2. And because they have the same tails, or the same endings, you can add them together as 11 root 2. So there's an important lesson to be learned there. That in terms of surds, like algebra, if they belong to the same surdal family, if they have the same tail, same ending, then you can add them and subtract them, no problem. So here's a question. If root 125 and root 20 is equal to k root 5, find the value of k. Now, first of all, take root 125 and root 20 and ask yourself, because they're quite large surds, can they be simplified? Is there anything inside 125 that's a square number, that's a factor of 125? The answer is yes, 25 is. So 25 will go into 125 5 times. So therefore 25 times 5 is 125, which means the square root of 125 is the square root of 25 times the square root of 5. What about 20? Does that contain a factor that's a square number? Yeah, 4. So that becomes 4 times 5, which is basically root 4 times root 5. And we're told to add them together. That is 5. Root 5 is irrational. We haven't a clue. Leave it as a symbol. Plus root 4, 2 root 5, which again we said we don't know. Add the two together because they have the same ending. They belong to the same surdal family. That gives you 7 root 5. And if you compare that up here, what does that tell you? 7 root 5 is equal to k root 5. So therefore 7 equals k, because the surds cancel. Done. Very simple algebra. Okay. Practice is the most important thing here. Now, let's simplify this one. So as I told you already, a lot of the stuff we do with surds is what we have already done with algebra. You cannot add or subtract algebraic terms unless they belong to the same group. You add x's to x's and y's to y's. In surds, it's the same. You add root 2's to root 2's or root 3's to root 3. So the surdal family is important. If the terms come from the same surdal family, then you can add them and subtract them, no problem. Go back to what we said in terms of multiplication for algebraic terms. If I gave you something like this, 5 plus 2x to be multiplied by 3 minus 7x. Everybody looking at this video knows what to do. The first term gets multiplied by both. Then the second term gets multiplied by both. Okay? It's exactly the same with surds. So let's take the first one. Root 5 times root 5. Now what happens when you multiply a root by itself? Root 5 by root 5 becomes root 25, which is 5. Okay, now there's a nice lesson to be learned in there. Whenever you multiply a surd by itself, it just becomes the number. So root 7 by root 7, 7. Root 11 by root 11, 11. Root 9 by root 9, 9. So when you multiply two identical roots, you simply lose the root and keep the number. Okay, so that's where root 5 by root 5 is root 25, which is 5. What about root 5 multiplied by minus root 2? Well, first of all, sort out your signs. Plus by minus is minus. Root 5 times root 2 is root 10. Any square in there that can simplify it out? No, leave it as root 10. Next one, we have the bottom 2 root 2 by root 5. Now, you can only multiply the surdal parts together, so that becomes 2 root 10. So you keep the 2, and you multiply the root 2 by the root 5 to get root 10. And finally then, that term by this one, which becomes 2 root 2 by minus, again, it's going to be minus 2. And then, what's root 2 multiplied by root 2? The answer is 2. Okay, so now tidy it up. Root 25 is 5. Minus root 10, nothing you can do. Plus 2 times root 10, and then minus 4. Now, they belong to the same surdal family. They belong to the surdal family root 10. So you can put them together. That gives you 5 plus 2 root 10 minus root 10 gives you plus 1 root 10 minus 4. And finally then, the 5 minus 4 is 1 plus root 10. And that's your answer. So again, multiplication of surds is exactly the same as multiplication in algebra. You take the first term, you multiply it by both the terms in the second bracket, then you take the second term and multiply it by both terms in the second bracket. Okay. Now again, I have this thing done out for you, so you can go down through that yourselves and have a look at it. There's the answer. So here's another problem. When a fraction involves a surdal denominator, what do we do? So if I gave you something like 3 divided by root 7, how do I divide by root 7 if root 7 is irrational and I haven't got a clue what its value is? The answer is you don't do division. You cannot divide by an irrational denominator. So in order to get around the problem, the first thing I have to do is to turn my irrational denominator into a rational denominator. Okay? Because at the moment, as it stands, I cannot divide by root 7 because I do not know what root 7 is. It's an irrational number. So, go back to the previous slide. What was the quickest way to turn any root into a non-root number? And the answer is to multiply it by itself. Root 5, when you multiply it again by root 5, gives you 5. Okay? So, in other words, when you multiply a root by itself, it comes out of the irrational state and it goes into the rational numbers, something we can actually use. So in this case here, here's what I know. If I'm dividing 3 by root 7, I cannot divide by root 7 because it is irrational. So what I'm going to do is I'm going to multiply root 7 by itself. And that immediately on the bottom is going to give me 7, which is rational. But I have changed the value of the fraction if I only multiply the denominator. See that? So if I multiply root 7 by root 7 on the bottom only, then I've changed. It's a brand new fraction. It's not the same fraction I started off with. So to combat that problem, if I'm going to multiply the denominator by root 7, then I also have to do exactly the same thing to the numerator, because in essence what I'm then doing is I'm simply multiplying by 1. And I'm keeping the fraction exactly the same. I might make it look different, but its value is exactly the same. So what's 3 times root 7? Well, do we know what root 7 is? No. So basically stick them together as 3 times root 7. And the answer then, root 7, is 3 root 7 over 7. So 3 times root 7 is 3 root 7. Root 7 by itself, drop the root, keep the number 7. Okay. And again, I have that done out for you there. So the quickest way, as we said already, to rationalize any surd is to multiply it by itself. For example, if you want to rationalize root 5, what do? You multiply it by itself and you get root 25, which is 5. So therefore, any root multiplied by itself will simply drop the root and keep the number, and that's important. But what about when the surd of the denominator is a fraction? And I've done this with you already, 11 over root 7. Now let's just take that one there. What am I going to do here? Well, first of all, 11 over root 7 cannot be done, because root 7 is irrational. So I'm going to multiply the denominator by itself, but in order to keep the fraction at the same value as it originally was given, I also multiply on top by root 7 as well. And I get 11 root 7 on top when I multiply the two top ones, and I simply get 7 on the bottom. Simple as that. Okay, and that's what I've worked through in this slide here for you. You can have a look at that yourselves. And there you go. 11 root 7 over 7. Now, the final part of this problem, or this puzzle, is this one. Rationalise the denominator of minus 4 root 5 over root 12. Let's just increase the complexity a little bit. Then there's one more example I want to do after that. Then I'm going to leave you off to do some of these things yourself. Because really, at the end of the day, I know I keep saying it to you, practice, practice, practice. That's what's going to make perfect. So, minus 4 root 5 over root 12. What's the problem here? The problem here is that I cannot divide by root 12. Okay? Because root 12, if you want to put it another way, root 12 is also the same as 2 root 3. Because don't forget, 12 contains 4, which is a square number by 3. So therefore, root 12 would be root 4 times root 3, which would be 2 root 3. Okay? So if you wish, you may put in this as a simplified form. You don't have to when you're rationalizing the denominator. It's not necessary, but if you want to do it, you can. Okay, I'm just showing you where I'm getting 2 root 3 from. Okay, what I would prefer to do is this. I'm not going to divide by root 12. So what I'm going to do is I'm going to rationalize root 12 by multiplying it by itself. And if I do that on the bottom, I have to do it on the top. So let's take the bottom first. Root 12 by root 12 leaves you with the number 12. Now watch carefully here. Minus 4, leave it, multiply the two surds together, root 60. And then check and see, is there a square number that is a factor of 60? Okay, so go through all the square numbers. I think 4 is the only one that actually goes into it as far as I know. 60 is not divisible by 16, I don't think, no. And it's certainly not divisible by 25. So if you just go up along your squares, 4 will go into 60. 4 goes into 60 15 times. Okay, so therefore I'm going to now tackle this. I'm going to simplify this a little bit. So minus 4 by root 4 times root 15. See? All over 12. Okay, let's start to simplify. Minus 4 by 2 root 15. All over 12. Now, minus 4, or I should say 4 goes into 4 once, 4 goes into 12 3 times. So what do I end up with? Minus 2 root 15 over 3. So not only do you do the multiplication, you also have to do the simplification afterwards if you see the presence of a large surd. And always, when there's a large surd present, always check and ask yourself, is there an easier way to write this? Okay, and you've discovered there is. Root 60 is also known as 2 root 15 because it's root 4 times root 15. Root 4 is 2. Root 15 we don't know, so therefore we just leave it alone, and you end up getting root 15. 2 times root 15 by minus 4 over 12. Do your simplification. Minus 2 root 15 over 3. Okay. Now, if the denominator includes a surd which is in a sum or a difference, for example 5 minus root 3, then we have to engage what is called the conjugate. Okay, now you haven't met this before. This is new, and this is going to be used again later on when we're dealing with complex numbers. But for the moment, if your denominator has a surd, there it is, root 3, that's a part of a sum or a difference. Now, it's not good enough to just multiply across by root 3, because I multiply across by root 3, it's also going to multiply the 5 as well, and the surd will remain behind. So what we've discovered is this, that when you take any sum or difference, okay, that includes a surd, if you multiply it by what's called its conjugate, the conjugate is the term that rationalizes a sum or a difference that contains a surd. Now, what do I mean by that? Well, first of all, let's just take the example I have here. Let's take 5 minus root 3. If somebody said to me, rationalize that, because the surd is a part of a sum or a difference, I multiply it by its conjugate. Now, look at what I say here in the second line. The conjugate of any sum or difference is, the middle sign has been changed. So the conjugate of x plus y is x minus y. So therefore, the conjugate of 5 minus root 3 is 5 plus root 3. So if I want to get the conjugate of a sum or a difference, I just change the middle sign. And then what I do is the normal multiplication, like algebra. First by first, 5 5s, 25. First by second, plus 5 root 3. Second by first, minus 5 root 3. And then minus by plus is minus. Root 3 by root 3. What happens when you multiply the same surd? You lose the root, you keep the number. 3. Look at the middle. Plus 5 root 3, minus 5 root 3. They cancel. 25 minus 3, 22. So I've now gone from 5 minus root 3, which is irrational, into 22, which is rational. So we are still rationalizing a sum or a difference that contains an irrational surd. Okay, so keep that in mind. So that is it. That's 22. Okay, so the conjugate, and again, look, minus 4 plus root 3. What's the conjugate of that? Minus 4 minus root 3. You only change the middle sign. So just be careful. Just the middle sign. Doesn't matter what sign is at the beginning. You aim for the middle sign. You change the middle sign. And then that is this conjugate that you multiply by in order to rationalize the surd that is part of a sum or a difference. So let's take a look at this one here. Rationalize the denominator of 2 minus root 3 over 2 plus root 3. Now, rationalize the denominator. So what I'm going to do here, it's not good enough for me just to multiply across by root 3, because the root 3 is part of a sum. So because it's part of a sum, I'm going to engage the conjugate. And the conjugate of the denominator, 2 plus root 3, is 2 minus root 3. And again, the same rule. If I multiply the bottom by 2 minus root 3, I've got to multiply the top by 2 minus root 3. And let's do our multiplication. 2 times 2, 4. 2 times minus root 3, minus 2 root 3. Minus root 3 times 2, minus 2 root 3 again. And minus root 3 by minus root 3 is plus 3. Okay, so do your signs first. Minus by minus is plus. Root 3 by root 3 is 3. So there's your top line done. Now do your bottom line. And this is where you've got to pay attention, because we want to rationalize the denominator. So we're working, hopefully, to get the bottom number down to a real number, or a rational number. So 2 times 2, 4. 2 times minus 3, minus 2 root 3. Root 3 times 2, that becomes plus 2 root 3. And finally, plus by minus is minus. Root 3 by root 3 is 3. Now tidy up the top and the bottom. 4 and 3 is 7. Minus 2 root 3 minus another 2 root 3 is minus 4 root 3. Okay, because it's just like algebra. If it was minus 2x, you'd have minus 4x. Just treat the surdal tail as the family of surds it belongs to. Okay, and then underneath that, what do we have? Well, first of all, 4 minus 3 is 1. And then minus 2 root 3 plus 2 root 3 cancels. So the answer comes out as 7 minus 4 root 3. And that's how you rationalize the denominator when the denominator contains a surd which is part of a sum or a difference. Okay. Now again, that's there for you. You can have a look at that in your own time. Page 183, question 9, part 9. Rationalize the denominator of. Okay, now this is the last one I'm going to do before I set you some questions to do yourselves. 2 root 7 minus 3 root 3 over 5 root 3 plus 4 root 7. Okay, rationalize what? The denominator. So straight away, I want to multiply this fraction by the conjugate of the bottom term. And the conjugate of the bottom term is 5 root 3 minus 4 root 7. So you just change the middle sign. So 5 root 3 minus 4 root 7. And I replicate that up on top as well. 5 root 3 minus 4 root 7. Because in essence, what I'm really doing is multiplying by 1. So I'm changing the appearance of the fraction, but I'm not changing its value. And then take your time and multiply. First term by first term. Now be careful. 2 5s are 10. And root 7 by root 3 is root 21. So you multiply the two outside parts, 2 5s are 10, and then the two surdal parts to give you 10 root 21. And then the next part, this one here, 2 root 7 by minus 4 root 7. What's that going to be? Now be careful, watch. 2 times minus 4 is minus 8, but root 7 by root 7 is 7. Okay, So I'm just taking my time doing these really slowly until you build up a head of steam when you do a lot of practice on them. Then take the minus 3 root 3 and multiply it by both. So minus 3 by 5 is minus 15. And root 3 by root 3 is 3. And finally, minus 3 root 3 by minus 4 root 7. Well, minus by minus is plus. 3 fours is 12. And root 3 by root 7 is root 21. Apologies, didn't mean to make that symbol there. Root 21. So root 21. So look at it again. Minus by minus is plus. 3 fours are 12. Root 3 by root 7, root 21. There's the top line taken care of. Let's do the bottom line. 5 root 3 by 5 root 3. Now, first of all, 5 fives, 25. Root 3 by root 3 is 3. 5 root 3 by minus 4 root 7. 5 times minus 4, minus 20. 3 times root 7, root 3 times root 7, root 21. Take the next one. 4 times root 7 by 5 root 3 becomes plus 4 fives, 20. Root 7 by root 3, root 21. And finally, 4 root 7 by minus 4 root 7 is minus 16. So 4 fours are 16 times root 7 by root 7, 7. And all you've got to do now is tidy up. But what you should notice immediately in your denominator is minus 20 root 21 and plus 20 root 21 cancel. Okay, what have I got on the top? I've got 10 root 21 and 12 root 21, which is 22 root 21. Okay, and then I've got 7/8, which are 56. Let me just do this properly. So minus 8 times 7 minus 15 times 3. Don't take any chances with these things. So this comes out on the top line as minus 101 plus 22 over 21. So the 10 root 21 and the 12 root 21, because they have the same surdal tail, they can be put together as 10 plus 12, which is 22 times root 21. So that's the top line done. Bottom line, well, 25 threes, that's 75, minus 16 times 7, which works out as minus 37. And that's it. Okay, so 25 times 3 is 75, and 75 minus 16 times 7 on the calculator comes out as minus 37. And that's your answer. That has rationalized the denominator. And as long as your denominator has gone from being something containing irrational surds into a real number or a rational number, then you have finished the exercise. Now, could you simplify this any further? Well, that's up to yourself. Unless minus 37, there's an all or nothing rule. Unless 37 will cancel with both the 101 and the 22, then there's nothing you can do. And this doesn't, because 37, 101, 22, they don't have any common factor. So that is the final answer. Okay, so I'm going to leave the rest up to you. I'm going to leave you with these ones. Page 183, question 2, 3, 7, 8, and 9, all based on what I've done in the previous half hour. So again, if you want to rewatch the video, or if you want to try and tackle these and then just go back and find where the examples of those type of questions are, by all means do. If you're stuck, email.